Hawaiian Islands represent massive oceanic shield volcanoes constructed directly on weak seafloor crust, each rising approximately 13 miles from ocean bottom to summit, before inevitably succumbing to gravitational instability. Mauna Loa demonstrates ongoing seaward creep, while Kilauea spreads laterally at measured rates of 4 to 10 centimeters annually. Steep flanks develop over weak structural layers composed of alternating massive lava flows, unconsolidated ashfalls, and fragmented pillow lavas formed during submarine eruptions. These internal weaknesses ensure eventual catastrophic failure under the volcano's immense earthquake-generated tsunamis result from continental-scale fault ruptures, producing coherent wave, with Japan's Arling Iyi Tohoku event achieving maximum local run-ups around 40 meters, despite thousands of kilometers of fault displacement. Landslide tsunamis operate through fundamentally different physics. Localized but extreme water displacement. Windiest to 100 cubic kilometers of rock detach from a volcanic flank and accelerate downslope into deep ocean basin at velocities reaching 50 to 100 meters per second. Ocean response differs dramatically from fault rupture. Water does not simply ripple outward. It heaves violently upward, generating radial wave trains exploding symmetrically from impact zone with initial amplitudes, exceeding model predictions for normal tectonic events. Primary evidence emerges from Nuuanu landslide scarring, Oahu's northeast flank, one among Earth's largest documented submarine failures. Debris field blankets 23,000 square kilometers of Pacific Sea. Individual displaced blocks, including Tuscaloosa Seamount, measure 30 kilometers long, 17 kilometers wide, rising 2 kilometers above surrounding bathymetry. Headwall scar spans 50 kilometers wide across Oahu's submerged flank. Numerical hydrodynamic models calibrated to this volume and geometry consistently demonstrate initial wave heights surpassing 100 meters immediately adjacent to collapse site. Neighboring steep volcanic islands like Lanai and Molokai experience extreme amplification through shoaling wave. Period remains conserved, but wavelength compresses dramatically, concentrating energy upward by factors reaching 2 to 3 times baseline amplitude or greater. Hulopoe landslide offshore Molokai exhibits comparable scale signatures and temporal correlation with high elevation deposits. Multiple candidate failures align through shared physics governing volcanic island instability. Discovery unfolded during 1980s geological mapping across Lanai when field teams encountered Hulopoe Gravel anomalous sedimentary unit capping exposed ridges at elevations spanning 326 to 370 meters above modern sea level. Unlike typical beach sands or thin storm veneer, this formation comprised metestic class-supported chaotic breccias containing coral heads, weighing 1.25 metric tons, each alongside limestone slabs, angular basalt boulders, and mixed marine faunal assemblages, representing both shallow reef environments and deeper oceanic basins. Diagnostic sedimentary features included pronounced imbrication, where larger clasts aligned with long axes oriented directly uphill toward island interior. Vertical grading patterns indicating heavier material settled first during single, high-energy depositional event, and remarkable lateral continuity, spanning multiple square kilometers across diverse topography, including ridge saddles and slope breaks, rather than exponential thinning characteristic of storm washover deposits. Molokai preserved identical signatures, marine gravel breccias perched above world's tallest sea cliffs, exceeding 1,000 meters elevation. Oriented directly upslope, facing open Pacific exposure, containing mixed shallow water reef corals alongside deeper water benthic fossils. Preserved precisely where neither storm surge nor tectonic tsunami possesses sufficient energy for emplacement. Initial skeptical interpretations invoked tectonic uplift, suggesting ancient shorelines elevated through island However, Hawaiian archipelago demonstrates net subsidence rather than Pleistocene reef terraces ringing multiple islands confirm systematic sinking over relevant timescales. No plausible mechanism exists capable of elevating former beach deposits 300 meters asymmetrically while simultaneously erasing all associated wave-cut benches, emergent terraces, and drowned coastal morphology that should accompany such dramatic differential motion. Extreme cyclonic storm surges offered second hypothesis, but impose strict physical limits. Maximum documented run-up remains under 15 meters, even during most violent tropical cyclones, with deposits thinning exponentially inland within mere hundreds of meters, while incapable of transporting multi-ton coral heads across major topographic divides, or maintaining thick, coherent, laterally persistent units spanning square kilometers of complex terrain. Resulting sedimentology and preserved energy signatures fundamentally mismatch observed field relationships. Only offshore volcanic flank collapse, followed by megatsunami propagation, satisfies complete observational suite, including deposit elevation, lithologic mixing, sedimentary fabric, topographic distribution patterns, and paleontological content. Collapse mechanics proceed rapidly through distinct phases. Volcanic flank spanning tens of kilometers width detaches along basal surface, exploiting pre-existing weak layers. Accelerates downslope, attaining freeway equivalent velocities within seconds. Impacts deep ocean basin, generating dual vertical and lateral water displacement, forming radial wave train, chaotic, disorganized near immediate source, progressively more coherent, propagating outward. Waves encountering neighboring island bathymetry experience extreme shoaling transformation. Steep volcanic submarine profiles preserve incident wave period, while compressing wavelength dramatically, forcing energy concentration upward through water column. Field-based conservative minimum estimates place Lanai run-up exceeding 170 meters, based solely upon lowest confirmed marine material elevations. Maximum interpretations, incorporating highest mapped outcrops, coupled with preserved flow trajectories, extend 300 to 425 meters vertical excursion. Multiple surge pulses manifest through patchy deposit distribution, striking both windward and leeward exposures. Differentially mixed shallow reef alongside deepwater benthic faunas, indicating wave trains sequentially sampling varied seafloor depths during propagation, and selective topographic scour patterns precisely matching computed wave refraction trajectories around island group. More classic mega-tsunami behavioral fingerprint preserved intact. Geochronology converges precisely upon late Pleistocene timeframe, approximately 100,000 to 120,000 years before present. Uranium-thorium radiometric dating applied directly to coral fragments preserved within high elevation. Breccia's yields ages falling squarely within this temporal window. Event timing correlates directly with major documented Hawaiian flank failures, including Nuuanu and Walo landslides documented through submarine bathymetric mapping and sediment core analysis. Multiple independent chronological constraints align without contradiction. Recurrence potential remains unequivocal geological certainty rather than speculative possibility. Kilauea volcanoes, south flank, exhibits demonstrable contemporary instability creeping seaward at continuously monitored rates, average 4 to 10 centimeters annually through combined co-seismic rupture and a seismic slow slip. Mauna Loa continues active growth phases. Recurrence intervals governing such extreme flank failures span tens to hundreds of thousands of years positioning. Events beyond immediate human hazard, timescales like annual hurricanes or decades, earthquakes yet representing fundamental geological inevitabilities shaping island chain morphology. United States Geological Survey, Hawaiian Volcano Observatory, maintains continuous surveillance encompassing flank motion through GPS networks, deep seismicity arrays, INSAR satellite, interferometry, and ocean bottom pressure sensors. Comprehensive warning infrastructure exists linking observatory directly to civil authorities and Pacific Tsunami Warning Center. However, inherent collapse dynamics unfold over literal minutes rather than days or weeks, limiting practical lead time between failure initiation and destructive wave arrival at populated shorelines. Modern impact assessment reveals existential regional consequences. Oahu North Shore experiences complete obliteration, sweeping entire coastal developments into open ocean. Honolulu low-lying districts flood through second-story elevations across metro area. Generated wave train propagates across Pacific Island, chain carrying destructive energy sufficient for regional coastal inundation, while distant, far-field remain manageable through existing alert systems. Mountaintop coral breccias constitute neither decorative anomaly nor geological curiosity. These formations represent ancient catastrophe warnings permanently carved into island topography. Human paradise constructed directly atop slumbering volcanic giants whose flank instabilities operate beyond mortal control or prediction. Next, inevitable failure arrives without mercy, announcement, or discrimination between tourist resorts and uninhabited ridges. Subscribe BayamTube immediately. Decode geological whispers, manifesting through submarine scars and mountaintop. Rubble before transforming into roars, capable of burying islands beneath their own displaced ocean.